All right, now we move on to section 5, types of chemical reactions. And in this section, there are 5 different generalized types of chemical reactions. And then in section 6, there's a 6th one. I don't know why they're not in the same, but there are 6 generalized reaction types that we need to discuss. The first of which is a combination reaction. In a combination reaction, 2 or more elements or compounds react together to form fewer products. Usually it'd be 2 reactants combining to make 1 product, as you can see here. So you've got one compounder element, a second compounder element combining to make 1 product. And that product will be more complex because they've combined together. More complex than the starting materials. An example of a combination reaction could be I've got hydrogen reacting with oxygen to form water. So we've got H2O, and we need to balance it like that. That would be an example of a combination reaction. Another example that's given from your book, which is actually wrong because it's not really properly balanced, but they have S plus O2, sulfur plus oxygen, to make SO2, and that would be balanced. But the problem is that sulfur doesn't exist, and they even have it as a solid. It doesn't exist as a solid, it's just as a single sulfur atom. It exists as a polyatomic species, so it's actually going to be S6 plus O2. And yeah, it might make SO2, but we need to have 6 of those, which gives us 12 oxygens, so we would need 6 right there. That's the proper reaction. A decomposition reaction is the exact opposite of a combination reaction, where one reactant is split up into 2 or more simpler products. So you can see A and B there, and that's in one compound has been split apart into 2 others. An example of a decomposition reaction, we could take water and split it apart using electricity, and that'll give us hydrogen gas and oxygen gas, and you need to balance it so you get that. Or, and as you can notice here, hydrogen and oxygen are both elements, whereas water is a compound, so they're both simpler than the starting material. I could also take hydrogen peroxide, H2O2, react it with light. It's very reactive with light, which is why hydrogen peroxide is stored in a brown bottle to prevent light from getting in. But we get out of that water and oxygen gas. And now I have balanced it. 4 oxygens on each side, 4 hydrogens on each side. And another thing to notice is that we have made 2 simpler products here. The peroxide has 4 atoms bonded together in 1 molecule. It makes another molecule water, but it only has 3 of them, so it is simpler than the peroxide. And then we have the element oxygen. In a single replacement reaction, you have an element switching, so we say A, this element, switching with an element that's in a compound, B in this case. So A has replaced element B in the compound. And I have here an element switches places with another element within the other reacting binary compound, meaning it's just made up of 2 species there. All right, an example of a single replacement reaction could be if I take zinc metal and I react it with hydrochloric acid. Those will form zinc chloride and hydrogen gas. And there's your balanced equation. So the zinc has replaced the hydrogen. There's also a double replacement reaction where both species are binary. And then it says the positive ions of two reacting binary compounds switch places. So A is going to go and be with D, and C is going to go and be with B. As you can see over here, they both switch. These are both compounds, whereas in the single replacement reaction, we had an element and a compound. An example of a double replacement reaction is given from a previous example in this lecture, but we've got the two sodium phosphates, Na3PO4s, plus magnesium chloride reacting, and there's three of those, to make magnesium phosphate, Mg3PO42, and 6 sodium chlorides. And so you can see in this double replacement, the sodium, which was with phosphate, has been replaced by the magnesium. And the magnesium, which was on the chlorine, has been replaced with the sodium. And then the fifth type is a combustion reaction. It says here a hydrocarbon or a carbohydrate burns in the presence of oxygen gas to produce carbon dioxide and water vapor. So a couple examples, I could take hydrogen gas, react it with oxygen gas to make water. And that's not balanced, so I put a 2 in front of there to balance the oxygens and a 2 in front of that. That wouldn't even be a hydrocarbon, it's just hydrogen. I could take methane, react it with oxygen, and you're going to get CO2 and water. And we would need to balance this, but we've got 1 carbon on each side, we've got 4 hydrogens on the left, 2 on the right. Now we've got 4 oxygens on the right compared to 2 on the left, so you put 2 there. You could also do a carbohydrate, so let's do glucose, C6H12O6 plus O2 to make CO2 and water. And the way I would start that is with the carbons. You've got 6 on the left, 1 on the right. Now you've got 6 on the right. Now you look at hydrogens. You've got 12 on the left, 2 on the right. You can put a 6 in front of there. So now you've got 12 hydrogens. You've got 12 hydrogens. You've got 6 carbons on each side. Now for the oxygens, it's challenging because you have 2 molecules on each side with oxygen atoms. So let's add them up first, though, and see what we get. We have on the left we have 6 plus 2 for a total of 8. And here we've got 12 plus 6 for a total of 18. And I can do this little calculation and do 18 minus 6, and I get the 6 from there, because I don't want to change the carbons and I don't want to change the hydrogens. I get 12. 12 divided by 2, which comes from that 2 right there, is equal to 6. So if I put a 6 in front, I've got 12 oxygens plus 6 is 18, and we already had 18. And so here you go. This is a carbohydrate combusting, this is a hydrocarbon combusting, and then this is just hydrogen combusting. Those are the types of chemical reactions. So here's a summary of the types of reactions given in section 5. But there is still one more type, and examples of them. So combination A plus B to make AB, example being calcium and chlorine reacting to make calcium chloride. Decomposition, A and B decompose into A plus B. The example there would be iron 3 sulfide decomposing into iron metal and sulfur. That one again is actually wrong, but whatever. It changes the coefficients, that's all. Single replacement A plus B and C to make A and C plus B. The example they give there is copper reacting with silver nitrate to make silver metal and copper nitrate. Double replacement reactions is A and B plus C and D to make A and D and C and B. The example they have is barium chloride and potassium sulfate to make barium sulfate, which is a solid, and calcium and potassium chloride. The key thing to notice here is actually the fact that you get a solid. Aqueous and aqueous making a solid and aqueous. Here's your product that you would be collecting. Without the formation of a precipitate, that reaction wouldn't work because everything is dissolved in water. And so technically what you have here, and the book doesn't go into all these details, but you'd actually have a Ba2 plus aqueous ion plus 2Cl minus aqueous ions in solution. And you'd have 2 potassium 1 plus ions aqueous dissolved in solution, and then 1, just like there's 1 barium, sulfate 2 minus aqueous ion in solution. And they would just stay in solution unless there's a reason for them to react. And since, as we can see here, these two, when they come together, make a solid that is not soluble in water, you get that product. Whereas the potassium and chlorine, they can come together, but that compound is soluble in water, so it's not going to be anything we collect. And then the combustion has CXHY plus ZO2 to make XCO2G gas plus Y over 2 H2Os and energy. That's a weird way of writing it, but the example they have is methane plus oxygen to make CO2, water, and energy. Section 6 of Chapter 7 is oxidation-reduction reactions, which can be shortened to just say redox reactions. But in these reactions, electrons are transferred from one reactant to another, resulting in a change in oxidation state of both species. Now, the reason we call it oxidation and not something to do with electrons is because when they were first studying these types of reactions, they noticed that there were oxygen atoms going from one species to another all the time. Well, we later found cases where that doesn't happen, and oxygen atoms are not moved, or what we would know as the oxidation state of a species is not changed due to the reaction, whether it gains or loses oxygen sometimes. So it's really more about the electrons than it is anything else, but more often than not, a compound that gains oxygen atoms is getting oxidized. The atom or the species that is losing oxygen atoms is getting reduced. And so as you can see here, oxidation occurs when a species loses electrons or gains oxygens. As a result, the oxidation state of that species increases. Okay, so you might have noticed I just made a change in the way it was typed, but in reduction, a species gains electrons or loses oxygens. As a result, the oxidation state decreases. This actually had said there are electrons before, and I just noticed it, so I fixed it to say oxygens, as it should. And there's a nice mnemonic here that helps people memorize what happens. It's called oil rig, where oxidation is loss of electrons, and reduction is gain of electrons, oil rig. But if you're looking at oxygens, it's the opposite. Oxidation is gaining oxygens, reduction is losing oxygens. The reason we call it reduction is if I have something that's, let's say it's neutral in charge to begin with, and it gains 1 electron. Okay, in a reduction, they gain electrons. If we look at this mathematically by charge, you'd be saying 0 plus -1, which is really 0 minus 1, which comes out to -1. So the charge, or the number from beginning to end, has been reduced. Whereas with oxidation, if it's neutral and it loses electrons, if we look at that numerically, 0 minus -1, we have a negative of a negative, which makes a positive. So we end up with a +1 charge. So there, we're going from 0 to +1. We have not reduced, we have gained in oxidation state. We don't have a word for that, but it's called oxidation. So this picture here just shows you what happens. Oxidation is a loss of electrons, and so the electron is going from A to B. A gets oxidized, B gets reduced because it has gained an electron and it's charged. Its charge has gone either less positive or to negative, and so therefore the charge is reduced. Also, the number of oxygen atoms is reduced from substance B, whereas A would be gaining oxygen atoms at the same time. All right, so we've covered balanced equations, chemical equations, coefficients, combination reactions, combustion reactions, decomposition reactions, double replacement reactions, oxidation-reduction reactions / redox reactions, oxidation, products, reactants, reduction, and single replacement reactions in this lesson.